All right, well, everybody, thank you for being here today. It is my pleasure to introduce to you all Erick, who is going to talk to us about Cramer alpha random primes and the fundamental theorem of arithmetic.
Great. I am looking forward to giving the cut. I want to clarify at the beginning that if you saw the title, that's actually $14 with the Cramer alpha random primes. I'm going to probably actually spend more time talking about general analytic theory, analytic number theory motivations for that. So perhaps maybe a subtitle of the talk could be an invitation to analytic number theory. And I'm going to spend a good bit of time motivating a lot of the questions that might come up in an analytic number theory context, and then tie that to the specific topic of the talk. All right. So first question I want to ask is, let's see, I worded it here to make sure it sounds nice to see. How likely is a randomly chosen natural number to be prime? This is the motivating question that really started a good bit of analytic number theory. And this is an interesting topic because if you've ever looked at how the primes behave, they seem almost kind of random. So remember what the list of primes looks like. 2, 3, 5, 7, 11, 13, 17, 19, you can keep going. There doesn't seem to be any nice pattern to how often these appear. And in particular, there's not any nice way to really compute primes, not any extremely efficient way to compute them. A lot of times you have to check a lot of prime potential divisors and check that a number has no divisors to verify that it's prime. And the behavior of this feels sort of random. There's not any good asymptotics you can get from a first glance from doing these type of calculations. So in order to answer this question, I'm going to talk about something called density first. So let's instead ask a different question, a set of primes, because this is a pretty hard question to answer. Let's first talk about odd numbers. This is a lot easier. So different questions. How likely is a randomly chosen natural number to be odd? Anybody want to take a guess? It's not a trick question. It's really that easy. 50%, right? Sorry, you were going to say that, right, Ross? I'm sure you're going to say that. Okay, so then we should think, okay, what do we mean by this? I stated this in English. What do we mean mathematically? A randomly chosen natural number. Let's see if you could try to define what does that even mean, a randomly chosen natural number? Because there are infinitely many options. So, you can't choose them all with equal probability. All right, so if you think about it, if I choose a random number between 1 and 10, okay, I can choose each one of those numbers with probability 1 to 10. How do you choose a natural number randomly in sort of a uniform way? There's not a nice way to do this. So one way to make this concept precise is using the notion of density. And I claim, let's see, write this down. So the odd numbers have density 1/2 in the natural. So this is another way of saying the answer. We said the answer was 50%. This is an equivalent way of saying the same thing. And then we need to define what exactly do we mean by density. So normally if you say that set A is 50% of set B, what would that look like? Normally you would be saying something like, okay, think how many elements are in A, divide that by how many elements are in B, and you should get 1/2. Usually that's what we mean when we say this set is half of that set. Let's say A is contained in B. Okay, well, if you try to do that, over here you would have, let's see, count up how many odd numbers there are, divide by how many natural numbers there are. Well, that doesn't really make any sense, right? You'd have infinity divided by infinity. So we have to make sense of this, you have to do a limit. So let me write down exactly what this means. It means I'm gonna let's say, script O. This is not a number field or anything related to a number field. But this is let script O be the set of set of odd numbers. Set of odd natural numbers. Then I'm going to say that the density of this set, that is this D of O, is equal to a limit as x goes to infinity. Right, and then you need to count up how many odd numbers there are less than x. How many numbers less than x, just that n is in this set, and then divide by the number of how many numbers there are less than or equal to x. Which in this case, I guess the answer would, the denominator would just be 4 of x. I've written this in particular for the set O of odd numbers, but this, you replaced O with any other set, you have the same definition. This is the density of the set. And if you compute this limit for the odd numbers, you can verify indeed this limit is equal to 1/2. So this gives us a precise way that we can say that the odd numbers do have density 1/2 in the natural numbers. It's precisely in this sense. We define this notion of density and compute the density of the set of odd numbers. That's out 1/2. So with this motivation, you then might want to do a similar thing with the prime numbers. So you might ask, okay, if I compute this limit for the set of primes, what proportion do I get? So like maybe I expect proportion 1/10, maybe 1/10 of all natural numbers are prime. Or maybe 1/100, maybe 1/100 of all, 1% of all natural numbers are prime. It turns out the correct answer is 0. It turns out that 0% of all natural numbers are prime. In this sense, so if you take density of the set of prime numbers, you'll get density 0. But we can actually be a little bit more specific than just saying 0%. We can sort of calculate, well, we can calculate the density within certain ranges, but let me make that more precise. So let me rewrite this expression. So another way we can equivalently say the same thing is that the odd numbers have density 1/2. This means that you take how many odd numbers there are up to the point x, and you can say this grows like 1/2 x. This tilde here just means the quotient of these two sides tends to 1. If that doesn't make sense to you, don't worry about it. Just think that this relation means it grows approximately like. So this is a function of x. This tells you how many odd numbers there are up to x, and I claim that this density result is equivalent to saying that the natural numbers here grow like, the number of odd numbers up to x grows like 1/2 x. So there, up to x, there are x total natural numbers, and the number of odd natural numbers up to that point is 1/2 x. We can do an analogous thing for the prime numbers. And so to answer this question, the answer to this question is, or I guess I should say, rephrasing this question, will determine the growth rate it's called pi of x, which is how many odd numbers there are up to x. So how many p less than or equal to x for p. Alright, so just like determining the, oh, sorry. Oh, I forgot to mention, right here, yeah, right here I wrote absolute values to be consistent. Let me write it like this. When I write a pound sign in front of a set, I'm just taking the magnitude of that set. So just like this expression, understanding the growth rate of the count, this is called the counting function. And computing the growth rate of the counting function for the odd numbers. Likewise, we can understand how the primes are distributed if we can understand this growth rate. So how many primes are there up to x? This was a very, very important question historically. There was a lot of work going into playing around with this function pi of x and trying to calculate explicit formulas for it, and trying to calculate the exact growth rate. The conclusion is something called prime number theorem. I'm just going to abbreviate as PNT in this article. Prime number theorem tells us what the growth rate of pi of x is. Prime number theorem says that pi of x grows like a function y of x. What is y of x? This is the function of an indicator. I'm going to go from 2 up to x plus 1 over log x. That's like 1 over log p. If you want to compare with this function, it's maybe not super obvious exactly how y of x grows. So it turns out y of x, in fact, grows like x over log x. So then if you want to compare with the density for odd numbers, the way you figure out the density of the odd numbers is you look at this coefficient in front of x, right? So half of all the natural numbers are odd. Here, you would say 1 over log x proportion of these numbers are prime. So up to x, the correct answer is what proportion of the natural numbers are prime up to x? The correct answer is 1 over log x. I'm going to give now another interpretation of this fact. Let's see, let me think about how I want this. Okay, so prime number theorem is the mathematically correct answer for how fast pi of x grows. Let me give you an intuitive answer. So I'm going to draw this in a thought bubble because everything I write in here is going to be non-rigorous. This is just for purposes of intuition. So you can say we're trying to figure out how likely is a randomly chosen natural number to be prime. Well, I could say if the primes behave randomly, then I'm going to write some things down that if you think too hard, you'll say, wait, I'm not sure that makes sense, but that's okay. We're still in our intuition bubble. So let's say probability, and let's say n is a random number. Don't think too hard about what random means here, but let's say just say probability that n is prime. And then I want to calculate what this should be. I think Dr. Quirkendall commented last time I gave a talk about my very powerful strategy of wishful thinking. This is another example of this powerful strategy in practice. So, okay, what does it mean for n to be prime? Well, that means that it can have no proper divisors. So that means that D does not divide n for all D between 2 and n. Right? You'd agree that's the same thing as being prime. If you've worked with prime sieving things before, you know you could actually replace this with square root n if you wanted to, and you can do that. It won't change much, but I'll just keep it like this for now. So probability that n is prime. It's probability that D does not divide n for these. How do I want to say this? So yeah, I'm gonna write it like this. I'm gonna change this code. So prime P does not divide n for all primes P. There we go. I like that. You'll see why I changed this thing. So for n to be prime, they can't. None of the previous smaller prime numbers you found so far can divide it. And we can. So this is a big and of a lot of different things. So this means 2 does not divide n, and 3 does not divide n, and so on. And then you can think, let's see, these are all different events. I claim that these are independent. Of course, we're in intuition land, so don't think too hard exactly about what I mean by independent. But if you pick a random natural number, whether or not it's divisible by 2, that should have no effect at all on whether it's divisible by 3. And those should have no effect on all whether it's divisible by 5, right? We know how unique factorization works, so those shouldn't have anything to do with each other. So at least staying within this intuition bubble, we can say these are independent. So we can say this is probability that 2 does not divide n times the probability that 3 does not divide n times ... all the way up to the last prime below n. And I'm gonna write this as a product. So this is product over all primes P less than n. Let's see, and probability that P does not divide. And I'm going to continue over here. Okay, now we can think, if you have a random natural number n, what is the probability that P does not divide it? Well, the probability that P does divide it should be 1 over P, right? If I pick a random natural number, there should be a 1 in 5 chance that 5 divides it, right? So this means that this probability could be P minus 1 over. Do you agree with this? So 1 minus 1 over P, equivalently. And I won't go through all the calculations right now. You'll have to take my word for it, that if you calculate this out, this is about 1 over log n. This isn't terribly difficult to show. It's not real quick. So within our intuition bubble, we just observed that if the primes behave randomly, probability that a natural number n is prime is like 1 over log n. Compare that with the prime number theorem. Prime number theorem says the number of primes up to x. Now this is an integral. So it's like we're adding up all the possible numbers between 2 and x with weight 1 over log t. So for all t between from 2 to x, we're adding that number with weight 1 over log t. So in other words, this is predicting that the primes behave exactly as if they were randomly, as if they became randomly with probability 1 over log n. So if you took this as your motivation, you say, okay, if I choose a bunch of natural numbers, and I choose it to be in my set with probability 1 over log n, you would expect the counting function to behave exactly like this. You add up all possible numbers t, and you do it with weight 1 over log t. If you're concerned about integral versus sum here, that's not important. In fact, this grows the same as if you replace this integral with a sum. So that's not really relevant here. Okay, so I'm going to say that my interpretation Interpretation of the prime number theorem based on this argument is that the primes behave as if they appear randomly with probability 1 over log n. Because with probability 1 over log. Like this. I apologize. My handwriting gets worse because I try to cramp my head and goes above and forth. Because of this interpretation, one natural thing you can try to do is ask, if this is one interpretation of the prime number theorem, what if we actually did generate numbers that were generated randomly with the same probability? So let's do exactly that. If the primes behave like a set generated randomly with these certain probabilities, you choose n with probability 1 over log n. How would that set behave? This is what are called the Cramer random primes. Cramer random Cramer random primes are defined as follows. So define the independent newly random variables Cn, where probability that Cn1 is what I'm going to call new of n, and I'm going to use uppercase here. Uppercase n. I use lowercase n here, but to be consistent with some notation later on, I'm going to use capital N, which is just 1 over or uppercase. So 1 over 1. What does Bernoulli random variable mean? This means it takes the value 0 or 1, and it's used to indicate whether or not a condition holds. In this case, Cn is supposed to indicate whether I'm choosing n to be in my random set. So I'm going to say then the Cramer random primes. Oh, wait, so then A1 is defined to be set of all natural numbers. Set of all natural numbers such that Cn is equal to. So this is a randomly generated set. If you want to, you could equivalently set this up and just say, let A1 be the set of all natural numbers where n is chosen to be in the set with probability 1 over log n. That's exactly what I'm doing here. I just stated it here in terms of the language of random variables because that's standard in probability. This is just sort of how you make precise the sentence I just said verbally. There is one issue here, which is that if I'm going to say the probability is 1 over log n, I need 1 over log n to be between 0 and 1, which actually it's not. So I need to modify this slightly. So this needs to be 0, that equals 1, 1, that equals 2, and this is 1 over log n for n greater than 2. Okay, so let me explain to these. So if you plug in 1 over log 1 over log 1, that would be 1 over 0, so that doesn't make any sense. So we have to pick some probability that we're going to select n equals 1 to be prime. And it turns out we're going to talk about factorization in a minute, and factorization doesn't really work well if you have 1 be a prime number. So everything works much better if you choose n to not be a quote unquote prime. And then you should compute 1/log2, it's 1 point something, so I have to clip to be within the range 0 to 1. And then for the rest of the numbers, I can choose x to 1/log. This modification is not super important. Just know it's trying to be 1/log n, except in some cases I have to adjust for everything to be well defined. Okay, these I said it verbally already here. A1 is called the set of the Cramer now, if we've set this up correctly, then hopefully this random set we've defined should model the actual primes. Right, because remember our motivation here. We saw from prime number theorem that the primes sort of behave as if they were generated randomly. So if we actually construct a random set, we hopefully expect that this set should behave just like the primes. So you can ask lots of questions about these Cramer random primes. And you can ask whether they satisfy certain properties of the primes that we're familiar with. So the conclusion is for questions about distribution, the Cramer random primes turn out to do a pretty good job of modeling the actual primes. So for example, you could ask, do they satisfy something like prime number theorem? And the answer is yes. Hopefully they would, because that was the whole motivation for why we defined these. So they satisfy prime number theorem. You could ask, do they satisfy things like twin prime conjecture? All right, so this is an important question that people care about the primes that has to do with its distribution. So you could, one way to interpret the answer to this question is, okay, if the Cramer random primes satisfy the twin prime conjecture on average, then does that mean that the actual twin prime conjecture for actual primes is just sort of is true because it's just sort of happens to be true because the probabilities work out, or is there some fundamental structure that forces it to be true? Or is it just true by nature of how dense it happens to be? So you can ask all these sorts of questions. What are other examples? Gold box conjecture, right? This can be interpreted in terms of distribution of primes. So turns out Cramer random primes, they do satisfy gold box conjecture with probability 1. Well, and under a certain interpretation, I should say. There's some asterisks because we're dealing with probabilistic sets. Notes. The question I'm mainly interested in for the topic of this talk is how well do these random primes describe unique factorization? Right, because in some sense, this is the defining characteristic of the primes. This is the whole reason we define primes like we do. Is because you have fundamental theorem of arithmetic. Every natural number factors uniquely into primes. And I worded it like that because all allow multiplicity. So I won't say prime powers. When I say factor into primes, I'll allow multiple primes to be included in that product. I should let me remember that. So, well, fundamental theorem of arithmetic. Every natural number and factors uniquely into primes. Or parentheses allowing methods. So I was 12 is 2 times 2 times 4. That's my unique factorization of primes. I allow the factor 2 to be in here. And then our question is, how close does my random set, how close do the Cramer random primes come to satisfying fundamental theorem of arithmetic? Maybe interpreted another way. If we can answer this question, maybe we can get some insight into whether the natural numbers satisfy fundamental theorem of arithmetic because of some fundamental structure. Maybe it's just because of how dense the primes are, so it just kind of works out on average like that. I should also note that factorization is an algebraic property, and the Cramer random primes are designed to model the analytic properties of primes. In other words, distribution, how common they are. So it's not necessarily given that we would expect this sort of if I can call it analytic model, something designed to model the distribution of primes, that it would satisfy algebraic properties nicely. So this is another way to interpret this question is, given this analytic model, how well does it imitate algebraic properties? And now I'm going to modify everything I've written here. I want to actually generalize this slightly because I want to consider not just the Cramer random primes. I want to consider sets that are slightly less likely and slightly more likely for the primes. To do that, I'm going to add a parameter here. So instead of just considering log 1 over log n, I'm going to consider 1 over log n to the power alpha, which will always denote that like this, 1 over log to the alpha n. So just like we write sine squared of x, it's supposed to denote sine of x squared. So denote like this. And note, let's see, I should have enough room right here. So at alpha greater than 1, this means that this set is less likely than the actual primes. Less likely than x. And alpha less than 1. This is more likely than primes. In fact, I'm going to study this question for not just sets that are distributed like the primes, but sets that are distributed a little bit more likely and a little bit less likely than primes. All right, I need to make all the appropriate modifications. So I'm going to call this A alpha. The classical Cramer random primes come at alpha equals 1. So let's see, alpha is here, and then this would be Cramer alpha random primes. All this remains the same. So the Cramer alpha random primes have that condition. Let's change this one. Probably still the question about alpha equals 1 is probably still the best motivator, but we can also understand the select generalization. All right, let me check on this next time. Okay, good. That's how much time I was intending to spend roughly. So all of this is a lot of background. For the rest of the talk, I'm going to be specifically talking about this question and focusing on how we investigate Cramer alpha random primes. Since we already have this notion of density defined, I'm going to give one potential interpretation for how you could try to answer this question. So fundamental theorem of arithmetic says if you take you have a set of primes, you take all possible products from that set, and that gives you the set of all natural numbers. So what I'm going to do is, well, let me write it like this. So multiplicative closure. I'm going to write MULT for multiplicative closure. This is just the set of all products. So multiplicative closure of the set of primes this is exactly the set of natural numbers. So if we want to know how close does A alpha come to satisfying primes, then we should ask, how does multiplicative closure of A alpha behave? Does it make up all natural numbers? Maybe it's only 50% of them. Maybe we can only represent 50% of all natural numbers as products. Maybe it's 0%. So what do we expect should happen? Let's see. So for alpha less than 1, if you have my set of Cramer alpha random primes, for alpha less than 1, this set of primes is more dense than the actual primes. So hopefully I should expect every number to be able to be represented. I hope that every natural number should be able to be written as a product of this set, which is more likely than the prime. So for alpha less than 1, hopefully this equals all of n. For alpha greater than 1, less likely than the primes, I would probably expect it to not be all of them. Probably I'd have a lot missing. And this is the first big result of this talk. So, well, no, I can't say that. I'm talking about prime number theorem. This is the first big result that I worked on of this talk. There we go. Prime number theorem is a very big result. First big result I worked on in this talk. This theorem, right? With probability 1. Any probabilists in here will say, so almost surely. Yes, I know, but with probability 1, the set of all products of A alpha has density remember our notation for density, we have D of a set. So D of the multiplicative closure of A alpha is equal to this is 0 for alpha greater than 1, and it is 1 for alpha less than 1/2 log 2. But does this match what we expect? Let's see, in the case of alpha greater than 1, we have numbers less likely than the actual prime. So yeah, I would kind of expect that this set has density 0 in the natural. Remember, it's 0% of all natural numbers can be written as a product of Cramer primes. In this case, let's see. It would be better if I could improve this to all alpha less than 1. Right. So optimally, I think this result should hold true for all alpha less than 1, but I don't know how to prove it. I can prove that it holds on average, actually, but that unfortunately is not enough to get the full result. Okay, so yeah, that's one, I guess you could say, weakness, or one shortcoming of this result is that there's a pretty wide range that I don't know how to solve. I suspect it's going to be a much harder problem to figure out what happens at alpha equals 1. I think it's actually probably not, well, I was going to say it's probably not too terribly difficult to prove this for all alpha less than 1, but you know, I couldn't figure out how to do it, so I guess maybe I shouldn't make comments about how hard it is because I really don't know.
Did you assume Riemann hypothesis?
No, I did not, but I didn't see any way where that would lead into it. Okay. Any questions about this? I'm now going to talk about the strategy for how you might prove. Maybe you wonder where the half log 2 comes from. So let's see where the half log 2 comes from. I suspect that will take me to the end of the time. If I'm really quick at talking about this case, then I'll talk about this case as well. If not, that's fine. We can just focus on this.
Eric, can you say something about the multiplicative? So like the multiplicative closure of the prime? Notation.
So
Without that, like if you miss 2 and you miss 3, you're done. It's not gonna. So there's something intuitive that I missed about that was.
say this one more time.
Well, what's the closure part of the? It's something about the multiplicative closure of the set of products.
So let me write down more. So
You don't have to write it down. It's just intuitively. So
multiplicative closure of A is set. So for any set A, set of all possible products of elements in. So if you take A to be your set of primes, let's see, you're taking all possible products of primes. That gives all natural numbers. When I say you're allowed to repeat products. So yeah, all possible products. This is allowing repetition. Okay, in this case, we have another set. So let me give an example. So maybe a set A is 2. Maybe we have 4, 6, maybe 11, and you keep going. Then you can think about, okay, what would my set of all possible products look like? In this case, multiplicative closure of A, all possible products, let's see. 1 can be written as an empty product. And, well, okay. There's 2 different ways you can define this actually, whether you consider the empty product or not, but that's not really relevant.
it's measuring whether like the gap set has 0 measure or not, right?
Come again?
Is it measuring like if the gap set? So there's gonna be a gap set. That's right.
The answer is not necessarily, because even if you skip 3 here, you might be able to recover 3 later as a multiple of another number. So even if you have gaps like at small numbers, you can sort of recover the gaps later on.
Okay.
So in this case,
Oh, I see.
all possible products would be 1, 2, see 4. 4 can actually be written in multiple ways. I'll write this as a set, not a multi-set. If I was writing a multi-set, I would write 4, 4. Here, I'm working with sets. I'll just write this once. Let's see. 5 cannot be written as a product of these numbers. 6, let's see. Then the next number would be 8. So 7 cannot be written as a product. Let's see. 9 cannot, 10 cannot, 11 can. Let's see, 12 can, because 12 is 2 times 6. So notice we missed 3, but still we kind of recovered 12 later on. Does that answer your question about gaps? So if you work with these, you'll notice these tend to be kind of sparse for small numbers. They kind of, I'm going to be very big. They kind of fill out in a smooth way once you get large enough. So even though this maybe looks like it's not going to take a lot of natural numbers, everything sort of smooths out and it will typically have a density. To show the claimed result for 1/2 long 2. To show the second part of this, the density is 1. It suffices to show that the probability of a number not appearing tends to 0. It suffices to know plus. Probability. I gotta check my notes and I'm sure I'm wasting it wrong. Yeah, this is correct. So there is a short argument you need to use to say to prove that it does suffice, but I think this is sort of intuitively clear that if the probability tends to zero that's what I was calling. Probably and is not in this set tends to, yeah. So this means that it's very likely that every natural number will be in this set, and you'll end up having that the density is 1 with probability 1. Okay, I wrote down here A alpha squared instead of multiplicative closure of A alpha. What does A alpha squared mean? This is just all possible products of sets of elements in A alpha, of two products of 2 elements. So A times B, where A and B are both A alpha. So A alpha times A alpha, if you prefer that notation. And yeah, maybe I'll put that. Maybe that's so A alpha. Notice this is very, very inefficient. I'm going to prove a result about the multiplicative closure, the set of all possible products, by only considering products of 2 elements. So this tells you that probably this argument should be able to be improved a lot. In particular, I think you should be able to improve this bound pathlog 2 quite a bit. I think all the way to 1, but I don't know how to do it, and I've tried many times. So the argument I'm going to give seems very wasteful, but I don't know how to get rid of the waste. So suffice to show that the probability that n is not in the set tends to 0. Right. And we show, right, probability. I should win. I'm going to write a lot of formulas. Don't get too bogged down into the details. Try to see the bigger picture. So I am going to write a lot of things on the board, but all of this has an intuitive meaning that you can understand. So just think, we're trying to show that not appearing in this set is very unlikely. That's so, in other words, to be specific, and not appearing in this set tends to 0. Of course, this is as n gets large. And so for n to not appear in this set, notice what this would mean. This would mean that every possible way you can write n as a product of 2 elements, that product doesn't work. Okay, so in other words, it says product that B does not work, so B is not an element of A alpha, or n over B not element of A alpha. This is for all these. Okay, what is this saying? I'm trying to parameterize all possible ways you can write n as a product of 2 natural numbers. And say, okay, well, one way that n could be in my set would be if D and n over D were both in the set. And then the complement. So in other words, that means that for n not to be in the set, each one of these has to fail. So either D has to not be in my set of pseudo primes, Cramer alpha random primes, my set modeling the primes, or n over D has to not be in this set. And I'm gonna write the same thing, but only I'm gonna restrict the number of divisors I consider for technical reasons that you don't need to worry too much about. It would be non-element A alpha for all divisors for all B dividing n, and then D needs to be between 3 and square root. Don't really worry too much about this. Just know I'm considering a smaller set of possibilities. So I'm allowed to do this. I'm only going to think about divisors within this range. And then the reason I do this is because then notice each of these events is independent. So I have these different events for all possible divisors of n. But notice, since I restricted D to this range, D not falling in my set or n over D not falling in my set. If you think about how the factorization works, since D is less than square root n, all of these events are independent. In other words, we have no overlap. Let me give an example. So, let's see, if I had n equals 36, then let's see. Then instead of all d dividing n for 3 plus the square root of 36. In other words, I'm trying to write 36 as 3 times 12, 4 times 9. Let's see, and then okay, I guess 6 by 6 would not be counted since I'm only taking divisors less than the square root of n. I guess this is sort of a small example. So it's kind of hard to see. You see, the fact that I stop before I get to the square root of n means that none of these numbers in here are repeated, which means whether or not they fall in this set, these are all independent events, which means I can rewrite this as a product. Remember, for independent events, the probability of an intersection is product of the probabilities. This is 3 less than d square root of n. This is over divisors of the event. D dividing it. Then probability that d is not elements of a alpha or d is not an element or sorry, over. Not an element. Then I should use brackets. That's what I use. This is the step that I don't know how to deal with when I consider larger products. So the most natural, I think, thing to do if you were trying to improve this bound would be, well, what if here I got this bound by considering all products of 2 elements, just consider all products of 3 elements in A alpha. Problem is, if you do that, there's no nice way that I could figure out at least to parameterize this so that all of your events were independent, so you could break it up in this product like this. Maybe some of you are more clever than me and you can figure out a way to do it. You should let me know. Then we can make this result even better. We have this. Then you calculate. This is the product over each possible divisor of d. 1 minus 1 over log to the alpha d times 1 over log to the alpha n over d. All right, you can check this, take the complement, turns into an and. It's a product of 2 things, take the complement again. Straightforward probability calculation. You can see where these are coming from, right? So 1 over log alpha. Note this is also why I restricted to d being greater than or equal to 3. It just simplifies this slightly. I can write that mu of d on probability here is actually 1 over log L. You can convert into this more. And then I'm going to take the negative logarithm. This maybe seems surprising thing to do, but it's just for convenience. This then means that the negative logarithm of probability and not an element in A alpha. This means that it's greater than or equal to some logarithm 1 minus log alpha b The alpha. So how did this product turn into a sum? That's actually why I took the logarithm, because the log of a product is the sum of the logs. So logarithm works. And to show that this expression, probability tends to 0, that's the same as saying that negative log of that expression tends to infinity. So we've now converted this guy into a sum of these expressions, and we've reduced this problem to showing that a certain sum diverges. All right, and if you remember from your calculus class, we have different techniques for how to do this. If you remember Taylor series, you'll know that this is approximately the sum of 1 over log to the alpha d, 1 over log to the alpha n over d. And then you do a bunch more work. The rest of the work is analytic number theory techniques, which I'm not going to get into. But there are some interesting things that go into this, but for sake of time, I just want to comment that this is a big part of proving a lot of analytic number theory results, is figuring out how to work with a lot of these bounds and figuring out how to prove something diverges or that something grows faster than this other thing. And I'll just say ... and prove that this is greater or equal to, let's see. There's a lot of details on this. What are the alpha? 1/2 log the 2 minus epsilon and minus 3 log the alpha. Don't worry so much about where this epsilon came from, but you can do this. And then this tells you exactly where the 1/2 log 2 parameter comes from. Because remember, our goal in here was to show that this probability tends to 0. And to show this probability tends to 0, we need to show this sum tends to infinity. So to show that this guy tends to infinity, we need, let's see, look at what this expression looks like. We have log to some power of n, and then log to some power of n. We can get this to work. We can get this expression to tend to infinity precisely when 2 alpha is less than 2 minus epsilon. Wait. Sorry. Log 2. Log 2. So it's log n to the power of log 2 minus epsilon. So we need alpha to 2 alpha to be less than log 2 minus epsilon. And that's why we get this constraint over here. Alpha is less than 1/2 log. For these parameters of alpha, we can get this sum to, or this expression to go to. All right, it looks like I do not have enough time to talk about this expression, so I'll just say verbally. The way you can prove the density tends to 0 when alpha is greater than 1, which is the numbers appearing less likely than the actual primes. You can show this via a very detailed induction argument on the number of prime divisors, the number of Cramer prime divisors that a natural number has, and take an averaging result over that. All right, that is all. The end.
Questions?
Yes.
So like, I don't know if this is like, makes sense in question, but could anything like this work if you took just like a general, like, I guess, multiplicative monoid in the integers?
Well,
Like,
actually,
like,
so
had some distribution on the generators?
yeah, you could do the same thing. This is a multiplicative monoid on the natural numbers, by the way, with generators A. So there's questions I'm interested in answering about about that multiplicative modeling. I don't know most of the answers, but that is some things I'm thinking about.
Other questions? No, fine.
Have you thought about this in other, say, quadratic integer rings?
I have not. Sounds interesting.
Others?
Actually, I didn't know that.
Yeah.
Yeah, I quickly Googled Cramer primes and I saw that Terry Tao wrote something in 2019. I don't know. I was wondering if you could say a bit about the origin of this. Is this something that's been around the last 10 years that he came up with and now you're looking at this problem? I'm just curious as to like what the background is. This
I think
particular
it
problem.
was came up by, I think his first name is Harold Cramer. When did Harold Cramer live? I want to say it was sometime in the 20th century. I do not remember any more narrow than that. So my short answer is I don't remember how long. I think it's been a little bit of time that this has been studied. I mean, because the interpretation of prime number theorem, I think, is not too difficult to see.
But what sort of problems are they looking at? I mean, like this seems like a fairly standard thing to ask about that, but I'm wondering did this come up when they were looking at something, the remap or something else? And like, you're just like, hey, let's look at this
Right.
aspect of it.
Right. So actually, I'm quite surprised that this question has never been asked before. It seems like a natural question to me. I mean, the defining characteristics of the primes is fundamental theorem of arithmetic. So I would think you want to check this, but nobody has that I can find. There is. Okay, there's a lot we can say here. A non-probabilistic interpretation of this has been done. There's something called Bjorling generalized integers, which is numbers that are distributed like the primes, not randomly generated, but they're explicit real numbers that are generated like the primes. And you take all possible products, and then you ask questions like, does this satisfy prime number theorem and such? So that has been studied. The fundamental difference between that and what I'm doing here is that here you have to deal with a lot of multiplicity issues. So when for Bjorling generalized integers, they're only dealing with real numbers, which means that you essentially never have any overlap between products of different real numbers. There's never really going to be multiple ways to write a real number as a product of these generators. Whereas sort of the whole difficulty here is in dealing with these overlaps. So that's one potential direction. To answer your earlier question, what about earlier motivation? The earliest motivation for these was to understand, are the properties of primes we're seeing a result just of their density, or is it because of special structure? So yeah, I mentioned, I think, twin prime conjecture, you can check that. You can check Goldbach's conjecture, and there's several more. And they found that Harold Cramer and others after him found that most of the properties they checked that we're used to of the primes also hold for Cramer random primes, which in some sense you could interpret it as saying, well, then these properties of primes are just because of their distribution, sort of. There are, of course, some exceptions. This model does not predict all properties of primes.
Yeah, exactly. I figured if that was the original motivation, then this question should have been looked at, but
It should have been, I think, but
so I thought
I wasn't able to find anywhere that anybody asked about this. So I'm happy to oblige.
Is Harold Cramer the Cramers moved by the Parisian upper frame?
Come again?
Was it Harold Cramer who came up with Cramer of Tool, or did another Cramer?
Oh. Not that I know of.
I think the Cramer's book that was 19th century, wasn't it?
Yeah, so I think the answer is different person, but I'm not 100% sure.
It's not Cosmo Cramer. So that much I know. God, getting old, they don't even breaking out Seinfeld jokes. Other questions? Okay, let's take Eric.